In this final section, we want to talk about how to train a deep neural network. We'll go over this in more detail later, but we want to introduce you to the concept. So actually, it's not very different. We're still going to use the standard gradient descent, the stochastic version of it, by using backpropagation to be able to understand how individual weights in this very complicated network architecture influences our cost function by calculating the partial derivative of the gradient with respect to that particular weight. However, we're going to notice that the hidden layers closer to the input values have a smaller activation. And why do you think that is? You can see this in this network architecture here, in this blow-up, where we can see that the neurons closer to the actual output value have very strong activations, but the ones farther down in the network have lower activations. You can see their magnitude of their positive or negative values are quite a bit smaller. And we understood this as a community for a very long time when neural networks were first being explored. The problem was with our particular activation function. When we have an activation function, as we've talked about before, at a very extreme value of a signal, meaning very low, let's say something close to negative infinity or positive infinity, we get a behavior that saturates or is very close to a 0 or 1 value. When this happens, let's say we have a case out here, okay, the gradients are almost close to 0, but are not 0. They can still learn from this scenario because there is a gradient, but the gradient is very, very small. And this gets compounded the farther back in the network you go. So for example, when you're close to the top layer, we might be able to get a reasonable amount of gradient here. So we'll see something like this blue learning curve that we've illustrated here. But as we go towards the yellow curve, you can see it starts to get worse. Our gradients get more flat because the values that are being compounded get more and more positive or negative as we go backwards for the network. And in this case, for the second layer here, our gradients are starting to look a lot worse. And this only gets compounded as we get farther back in the network. For example, at the third layer back, we have the red layer here, which gets even less activation because, again, our compounding of the signal over layers is going to get more and more extreme. So the downside of this is the more layers you put in, when we use a particular nonlinearity function like the one here, the sigmoid or the hyperbolic tangent, we have troubles learning towards the front of the network because the gradient happens to vanish in the case of very negative values or exploding where the signal is very close to 1, so there's not much chance of improving the gradient, then we'll have problems learning. So earlier layers take magnitudes more time to train, and this really caused a big problem because we couldn't train the beginnings of our network. If these couldn't be trained, then we couldn't have a deep network at all. So how did people solve this? They realized that we need any type of nonlinearity, not necessarily one that had the probabilistic interpretation that we wanted for logistic regression. So we replace both of these functions, the hyperbolic tangent and the sigmoid, with a much more friendly function called the ReLU. So the rectified linear unit, which is very simple to compute. If you're given an input, let's say a signal, we either pass the whole signal through if it's a positive number, but when the signal is negative, we get a 0. So it has this plot just like this, which is a very simple idea. It's not subject to the saturation problem that caused problems with our negative and positive gradient because of this part over here, where the gradient is always 1, where the output is exactly equivalent to the signal. It's a very, very simple computation to make because there's no type of exponential or trigonometric operators. So it's very fast to execute, which is very important in deep learning to be very efficient over a large amount of data. And notice, because it has a very simple linear structure, it doesn't have any second or higher order terms in the cost function. So simple stochastic gradient descent without needing to approximate second order terms will work just fine. It does have one shortcoming though, and it is somewhat sensitive to learning rates. So this is a particular parameter, eta, that we're going to have to set through validation. In short, we still have a function that is piecewise differentiable, just not at this point, but we can arbitrarily define that to 0. And otherwise, it becomes a very simple computational function that doesn't have the same problems with this tangent and sigmoid because the gradient doesn't ever converge to a flat or exploding value. Another issue that we need to take care of is unsupervised pre-training of the neural network. The key issue here is that the larger the network is, the more parameters there are, and then the more local bumps that there will be in the cost manifold. So initialization is very critical. We want to establish values of the weights that are going to be generally close to the correct solution, much as what we did by using linear regression as a first step towards using perceptron learning algorithm to then fine-tune the weights. The idea is, again, to use some type of unsupervised learning to set the network going to encode useful features that we're then going to use in a supervised manner to attend to the specific task that we want to do. So the supervised learning is basically taking the weights that have been set by the original unsupervised learning and then fine-tuning those. There's also a nice regularization perspective too. This type of unsupervised learning that we're doing out here is in some ways a good surrogate for coming up with a good prior distribution for the inputs x. And any type of representation that's good for x, as calculated through unsupervised learning, would be a good way to represent p of y too, because at least the x component is going to be measured fairly well using the unsupervised learning portion. Another way we can do this is by using the network architecture to help us, and that's the idea behind sparse autoencoders. The idea is that we want to learn a compact representation of the input. So for example, here you can see in layers L1 and L3, they actually have the same amount of nodes. We have 6 nodes here for the input, and we have 6 nodes here for the output. The name of this game is to be able to take the inputs and successfully replicate the values in L3. That wouldn't seem to be a problem except for this layer 2, the bottleneck layer, which has fewer avenues, only 3 avenues to store the information compared to the 6 in the input or output. So the size is smaller in the middle of the network. And what this helps to do is the network will have to learn a set of weights and abstractions in this layer that's going to correctly reproduce the output, even though the amount of model complexity that I have in my inner model, this hidden layer here, is smaller than what's actually necessary to properly encode this. So we can think of the layer 2 as being some type of lossy compressive algorithm that's going to encourage us to embody a good representation in this smaller amount of space. It's also connected very much to the regularization techniques that we would usually use. For example, L1 regularization is basically saying that we encourage sparsity by putting an upper bound on the amount of weight that I'm allowed to use to both try to fit the model as well as to achieve a low penalty for sparsity. So when we use an autoencoder, we're basically using the same architecture as we had before. We're going to train a first hidden layer and then move to training additional layers. Each time we train a layer, we discard the output layer and then retain all of the features that we've had here. So here we have a good generalization of the network of features coming in directly for our first level representation. Then we can train the next level and try to train for this network and then throw away this one. And finally train the output layer. So again, discarding that layer that we used to train specifically this layer, and then aggregating this with a softmax classifier that's going to tell us whether or not the input is of class 0, class 1, and class 2 as 3 different output nodes. The result is a pre-trained network where all of our values for each of the layers has already been preset in this first step using the autoencoder. After we have this network with the weights normally set up fairly close to the solution, we can use normal supervised neural network training, which is basically backprop with specific fine-tuning results to get better results overall. The final innovation that was done for training deep neural networks was the key idea of dropout. Because NNs are so complicated, as you can see here, with so many directed edges, they can still overfit quite badly. That means they would give you a good training error, but it wouldn't generalize to give us low testing error. So we need some other form of regularization. One way to do it is to actually disable some nodes in the network. We call this dropout. So for example, in the right-hand diagram here, we've chosen a random die of flipping a coin and decided to turn certain neurons on and certain ones off. The off ones don't participate in the training here and might participate after another iteration in which all of these edges have a chance to reevaluate whether they make the 50% mark randomly or not. When we knock a neuron out, its value is held stable for that iteration, while the remaining variables get to change. When we rotate this over many different mini batches, we're basically exposing each neuron to a different portion of the data set to help realize more of a rich representation so that we won't have problems with generalization. In fact, this idea is very, very similar to the idea of a random forest as feature projection, as we'll see in the next couple of weeks from now. It's also key to remember we are going to do this type of dropout procedure during training only, but in the testing part of machine learning, we always want to use all of the weight. We wouldn't want to impair the model, but for generalization abilities. In summary today, we looked at deep neural networks. We saw that they were really equivalent to a bunch of stacked units where the units could be anything. They could be perceptrons leading to a MLP or multi-layer perceptron. They could be a general linear unit, which we would think of as a neural network. And in this case, there were 3 particular important innovations that led to the capability of actually doing deep learning. The creation of better algorithms that led to deep learning, aside from the hardware and nature of the availability of data. Specifically, we had better activation functions. We came up with better ideas to initialize our weights to an appropriate weight rather than trust random assignment. And we invented dropout to get an idea of exposing certain parts of our network to different portions of our data, so that when we go through the entire data set, different neurons are getting exposed to it and not all of them. This will help to regularize the work.